In this video, we're going to continue to look at trigonometric equations, so equations involving trigonometric functions. It's going to be a little trickier than the last one, but it should be okay. So let's just try to solve the following equations. So A, sine 2x equals root 3 over 2, answer in degrees we're told. And B, tan 3x equals minus 1, where x is between 0 and 2 pi. We can assume here we're going to answer in radians because the range for x is given in radians. So let's go ahead and try and do A. So it looks very similar to, well, they both look similar to A and B from the last video. The only difference is instead of sine of x, we have sine of 2x, and we just have to note that because it's important. So sine of 2x equals root 3 over 2, then we can remember this exact triangle. So I'm not going to explain this triangle too much because there's a video, it's called Exact Triangles, that explains it in detail. But essentially, if you can remember this triangle, then we know that the number that when we take the sine of it, we get root 3 over 2 is 60. This triangle is telling us that sine 60 equals root 3 over 2, because if you look at it, remember, sine is S-O-H, so sine equals opposite over hypotenuse. So sine of 60 equals the opposite to 60, which is root 3 over the hypotenuse, which is 2. So we therefore know that 2x must equal 60, because sine of 60 equals root 3 over 2. You could also just do inverse sine of root 3 over 2 on a calculator and you would get the same answer. But I like to try and use these exact triangles whenever possible because you don't want to rely on a calculator because you might not have one in certain situations, like in a test, for example. So we use this and we calculated that it's sine 60 that's root 3 over 2, so 2x must equal 60. Except remember, we talked about this in the last video, sine has a period of 360 degrees. So if 60 is an answer, we're not given a range for our answers like we are in part B. We're just told all x's that solve this equation, which means whenever you're not given a range for a trigonometric equation, you usually find there's an infinite number of solutions. So if 60 is one of them, then if we add any amount of 360 to it, we get another because that's the period of sine. So the sine graph is just going to repeat every 360 degrees and we're going to get back to the same place. So we say it's 60 plus 360k, where k is just any integer. So it could be 0, 1, minus 1, 2, minus 2. It doesn't matter. If you add any whole lot of 360 or subtract any whole amount of 360 to 60, you'll get another solution. But this is a solution for 2x. We want to solve for x. So finally, divide both sides of the equation by 2. So on the right-hand side, we have to divide both those terms by 2, and we get x equals 30 plus 180k. So that's a set of answers, but it's not all the answers, because let's look at a sine graph. Let's draw roughly where root 3 over 2 would be on our y-axis, our sine x axis. It'd be about here. And we can see we found one solution in this principal range from 0 to 360. So remember, you always check in this range to see if you found all the solutions. So we found one of them here, 60, and we've said that if we add or subtract amounts of 360 to it, we get outside of this range and we get another solution. But within this range, there is another solution that we don't get just by adding 360 to this solution. It's a different solution, and we can see it here. And well, if this solution is 60, this first one, that's 30 below 90. And because the graph is symmetrical, we have to go 30 above 90 to get this other one. Now 90 plus 30 is 120. So 2x could also be 120. And once again, I'm just going to say 120 plus 360k. It needs to become sort of second nature to just always remember to add amounts of 360 or 2 pi if you're working in radians to your solution when you have cos or sine, because that's the period of cos or sine, if you're not given a range, like we're not here. So once again, we divide everything by 2, and we get x equals 60 plus 180k. So these are our two sets of solutions. There are no other answers in this principal range, so we have found all the solutions. So we have to again, finish by saying what k is. If someone was marking this, if this was an actual handwritten answer that I'd submitted, they would be confused as to what k was. So I tell them that k is an integer, and this is just a shorthand way of writing k as an integer. We say k is in z with a double bar on the z. That represents the set of integers. Okay, let's try b, which is a little tougher because we have tan of 3x. So here we're going to look at another method where we substitute the 3x for something else. So let's call this tan of u equals minus 1 instead of tan 3x equals minus 1, where u is 3x. So we've changed the 3x to something a little simpler. We just called it u. But we also, if we're going to do that, have to change our range. So the range for x was 0 to 2 pi. So to get the range for u, well, we times everything by 3. So we get 3 times 0 is less than 3x is less than 6 pi. So if we just times everything in this inequality by 3, we get 3x, which is u, which is why it's a u, and then we get 0 and 6 pi. So the limits now are not 0 to 2 pi because we've changed to u. They're 0 to 6 pi. So let's try and solve. So we do u equals tan inverse of minus 1. So I take the tan to the other side. Now if I put this into my calculator, which is the best way to do it, I think you'll get minus pi over 4. But look at our range, 0 to 6 pi. This is not in the range because it's negative, it's less than 0. So all our answers have to be positive. So we can't use this, but we can use it to find the correct solutions. So I said this is not in the range. So let's have a look at a tan graph. Now hopefully you're somewhat familiar with a tan graph. It doesn't look like a sine or a cos graph. Instead of being a wave, it still goes on forever in both directions, but it's these distinct lines, if you like, these distinct curves that go, well, if this one here goes from minus 2 pi to 2 pi, and it goes from all the way down to minus infinity and up to plus infinity between minus pi over 2 to pi over 2. And then it repeats again. So the period of tan is actually pi rather than 2 pi. You can see that from minus pi over 2 to pi over 2, that's a distance of pi, we have this curve, and then after that it just repeats on both sides. So here's our line at minus 1, and we can see that the answer we got from our calculator, because it gives us the one closest to 0, it gave us this one, minus pi over 4. But this is no good because it's not in the range. So which ones are in the range? Well, we can see there's one further up to the right. It's here where I put this dotted line. And as I said, the distance here must be pi because tan repeats every pi rather than every 2 pi. So if we add pi to minus pi over 4, we get 3 pi over 4. Now this is in our range. It's definitely bigger than 0 and it's definitely less than 6 pi. So this is good. This is an answer, but it's not the only answer. Let's try sketching a bit more of the tan graph. So I've shifted up a bit, so now I've started at 0 and I'm going up to 2 pi. And I'll mark on the answer we just found, which was this one here, 3 pi over 4. We can see if we add pi again, we hit another one here. 3 pi over 4, add pi is 7 pi over 4. So great, that's another solution. Put that down, but actually we can keep adding pi until we get, well, if we get one that's bigger than 6 pi, that would not be in our range anymore. Now 6 pi is 24 pi over 4, because 24 divided by 4 is 6. If we keep adding pi, we get u could be 11 pi over 4, 15 pi over 4, 19 pi over 4, 23 pi over 4. If we try and add pi again, we get to a number bigger than 24 pi over 4, which is 6 pi. So that would be out of our range. We get 27 pi over 4, which is bigger than 6 pi. You could put it into a calculator. 27 divided by 4 is bigger than 6. So we're done. We just keep adding pi until we would no longer be inside the range we're given. So these are our solutions. We've got 6 of them. So let's clear this graph. And I want to finish this question by noting that these are the solutions for u. But u is equal to 3x. So these are actually all equal to 3x. So 3 times x can be any of these numbers, then we have to divide all these numbers by 3 to get what x is. That's pretty easy because they all have 4 in the denominator. If we divide by 3, we'll just get 3 times 4 in the denominator, which is 12. So they're all Same numerators but with 12 in the denominator when we divide them all by 3. And this is the final answer. You might notice that some of these fractions could be simplified. 3 pi over 12 and 15 pi over 12 could be simplified because there's a 3 in the top and the bottom, but I'll leave that to you. I'm just going to leave them like this.